All right, question 1 from the Unit 2 version B practice exam. This is from section 3.2, graphing polynomial functions. Now, the steps I suggest you to take were 3 steps. Step 1, list the zeros. So the zeros, remember, if it's in factored form, the zeros are the values of each x variable that would make the factor itself equal to 0. So if you plug -1 in for x, that makes -1 a 0. Here we have -2, so x equals -2. And then here we have +2. I also suggested you consider the multiplicity. Remember, multiplicity is how often each factor appears. So x minus 2 is squared, meaning x minus 2 appears twice. So this has multiplicity too. Any even multiplicity means that at this 0 or x-intercept, the graph is going to bounce. So here it bounces. Each of these factors appear only once. The highest exponent there is 1, so these have a multiplicity that are odd. Odd multiplicity means the graph crosses through the x-axis. Now the y-intercept is when you let x equal 0. So when you plug 0 in for all the x values here, we're going to get 0 minus 2, that's -2. -2 squared is 4, so I'm going to have 4. And then here 0 plus 2 is 2, so that's 4 times 2. And then here that's 0 plus 1, which is 1. And then we have this negative sign here. So that's really -4 times 2 times 1, which is -8. And then the degree, or rather I'm going to say end behavior, so we have 1, 2, this counts as 2 factors, 3, 4, so there's 4 factors, meaning this is a degree 4 polynomial with a negative leading coefficient. So a degree 4 polynomial, the end behavior, the left side and the right side are both going in the same direction. Because there's a negative sign here, that means the left and the right side are both going down, like that. So now we place our zeros. We have -1, -2, and +2. And then -8, their y-intercept. End behavior, left side's going down to -infinity, right side's going down to -infinity. So now, starting on the left side here, we cross at -2. We also cross at -1, crosses through. We're going to come down to our y-intercept. Now, if you recall in class, if there's an integer, like a whole number gap, between either zeros or a y-intercept and a 0, we got to plug that number in, because it may be that the graph goes down a little farther before it comes up. So we need to plug 1 in for all the x variables. 1 minus 2 is -1. -1 squared is 1. 1 plus 2 is 3. And then 1 plus 1 is 2. And then we have that negative. So -1 times 3 times 2 is -6. So 1 comma -6 is right there. And then when x equals 2, it says we're going to bounce off the x-axis. Like that. Okay, question 2, this is from section 3.1, where we talked about quadratics. So this quadratic function here is in general form. So writing in standard form, I'm going to do it by completing the square. So the method I showed in class is we're going to take this number, move it over here. So I'm going to add 3 to both sides. And then this 2 that's remaining from these two factors, I'm going to factor the 2. That's going to leave me x squared plus 2x. And now there's a spot here inside the parenthesis where I need to complete the square. So we have half of 2 is 1. 1 squared is 1. So I'm going to put a positive 1 here. Now we need to balance the other side of the equation. This 1 is eventually going to be multiplied by this 2. So it's really a 2 that was multiplied, or added rather, to the right side. So we need to add a 2 to that side. So now the left side is f of x plus 5. The right side is 2. And then x squared plus 2x plus 1 factors into x plus 1 multiplied by another x plus 1, or x plus 1 squared. And then we can move this 5 back over here by subtracting. So we're going to have f of x equals 2 times x plus 1 squared minus 5. Now this is standard form. It's also called the vertex form because using transformations that we learned about in section 2.6, we know that the vertex, which is usually at 0, 0, has been moved 1 unit to the left and then 5 units down. So the vertex is the point -1, -5 right here. And from here, what I suggested in class is just make a table of values. We already know that -1, -5, that's our vertex, is one of the points. We need 2 other points. We have to have a total of 3 points. I'm going to do x values that are around where the vertex is, like x equals 0. If I plug a 0 in for x, I'm actually not going to use the vertex form. I'm going to use what we started with. If both x variables are 0, that gives us a -3. So 0, -3, and then we can use the fact that a parabola is symmetric, meaning there's a line of symmetry down the vertex, so there's going to be another point reflected over there. Now, when it says find the minimum or maximum value, what they're saying is the vertex, but we need to identify it as a minimum or a maximum. In this case, it's a minimum value because it's at the bottom of the parabola. All right, question 3. Find all zeros of the polynomial. This could be from section 3.4 and 3.5. That was the main topic of both of those sections. Find zeros of the polynomial. And the same steps both times. Step 1 is to make a list of possible rational zeros. So that list is going to come from factors of -2, that's p. So p equals ±1 and ±2. Now q comes from the leading coefficient there, which is 1. So q is equal to ±1. So now combining this into p divided by q, we take all the values of p, divide them by 1, which is just going to give us ±1 and ±2. So that's a list of possible rational zeros. What we do now is choose numbers from this list and see if they prove to be zeros using synthetic division. If we get a remainder of 0, then we know that we have found a 0. So I'm going to start with +1. Synthetic division is using all the coefficients of each term. And remember, if there are missing terms, even if the constant is missing, you have to have a 0 in that place when you're doing synthetic division. I'm going to run it through the algorithm here. So it looks like 1 doesn't work. Let's try -1. Looks like -1 doesn't work. Let's try 2. So looks like we found one. X equals 2 is one of our zeros. But that also means we found a factor. If x equals 2, then a factor is, so from this we know that x minus 2 is a factor, and then these are coefficients of a factor that's 1 degree less than what we started with. So if we started with degree 3, these are factors or coefficients of a degree 2 or quadratic. So that's 1x squared plus 4x plus 1. Now, sometimes when we have a quadratic, we can easily factor it into 2 linear factors. This one doesn't factor. There's nothing that multiplies to 1 that adds to 4. So what we need to do is take this and use the quadratic formula. So x equals the opposite of b plus or minus the square root of b squared minus 4 times a times c divided by 2 times a. So then x equals -4 plus or minus the square root of 16 minus 4, it's 12. The square root of 12 is 2 root 3. And we talked about this also in class. You simplify an expression like this when you have a value here, here, and here. You have to have a value in all 3 spots that have a common factor. These all have a common factor of 2. So all of those are going to be divided by 2. So we have x equals -2 plus or minus the square root of 3. So then our zeros are x equals 2 and x equals -2 plus or minus the square root of 3. Okay, so question 4, this would come from section 3.5. Given zeros, we need a degree 3 polynomial. So degree 3 means we're supposed to have 3 zeros. We have only 2, x equals 3 minus I, and x equals 2. But what you need to remember is these kind of complex zeros always come in a pair. So if one of them is 3 minus I, then its paired factor, or zero rather, is x equals 3 plus I. So those are the 3 zeros. So then the next task would be to create factors. So if x equals 2, I'm going to subtract the 2 over, and that's going to be x minus 2 equals 0. So you take the equation for the 0, get the right side equal to 0, that becomes your factor. So we have x minus 2 is the factor. If we do the same thing for that 0, if we subtract 3 from both sides and then add I, then you can see here it's x minus 3 plus I is a factor, x minus 3 plus I. And then here, if we subtract 3 and subtract I, then you can see it's x minus 3 minus I. So there's 3 factors. Recommend that you multiply those two together first using the distributive property, x times x is x squared. X times negative 3, negative 3x. X times negative I is negative ix. Negative 3 times x is another negative 3x. Negative 3 times negative 3 is positive 9. Negative 3 times negative I is positive 3i. And then I times x is positive ix. I times negative 3 is negative 3i. And I times negative I is negative I squared. Now we cancel some opposite terms there. Ix, negative ix. And then if you remember, I squared is negative 1. So here we have minus negative 1. So this is a plus 1 that can combine with that plus 9, giving us a 10. And then those two 3x terms can combine to negative 6x rather. And then x squared. So that's a combination of multiplying these two factors together. That gave us x squared minus 6x plus 10. Now we got to multiply it with the x minus 2 to give us x times x, x cubed, x times negative 6 is negative 6x squared, x times 10 is 10x. Negative 2 times x squared is negative 2x squared. Negative 2 times negative 6x is positive 12x. And negative 2 times positive 10 is negative 20. So then we have p of x equals x cubed. We combine our x squared terms to negative 8x squared. We can combine the x terms into 22x and then minus 20 at the end. Question 6 is a kind of a culmination. We have find all the zeros from section 3.4 or 3.5, and then from the zeros we can write it in factored form, but then going back to section 3.2 we're going to graph this polynomial. So if you remember, the first question we did on this review is graphing a polynomial. Step 1 was to find the zeros. Well, this is not in factored form, so that's why we need to do part A and part B to find the zeros. Once it is, then we can find the y-intercept and then use the degree to get the end behavior. Both sides are going to be going up, but what we're missing are the zeros. So for part A, we need a list of possible rational zeros. Now, P is going to come from here. That's plus or minus 1, plus or minus 3. Q comes from there. That's plus or minus 1. So when we divide all the values of P by 1, we're just going to get plus or minus 1 and plus or minus 3. So now we test using synthetic division, and we list all the coefficients here. Again, if there's a missing term, put a 0 in its place for a coefficient. Okay, so we have x equals 1, which means x minus 1 is a factor, and then we have x to the third minus x squared minus 5x minus 3. So now we have a cubic or a degree 3 polynomial. So we need to keep using synthetic division until the remaining values here are the coefficients of a quadratic. So we're going to do synthetic division again. But we're going to do synthetic division on this smaller polynomial, not the original one. And let's go back to this list here of possible rational zeros. Let's try negative 1. Okay, it looks like we found that negative 1 is a 0. So if x equals negative 1 is the 0, then x plus 1 is a factor. And then these are coefficients of a polynomial that's 1 degree less than here. So this is degree 3, so then these are the coefficients of a degree 2. So this is going to be 1x squared minus 2x minus 3, and then I'm going to bring this factor down. So that's going to be x minus 1. So now we have x minus 1 times x plus 1, and then this quadratic, we're going to try to factor it into 2 more factors. If it doesn't, then that means we have to use a quadratic formula. But we can factor this into x minus 3, x plus 1, and then we have x plus 1 and x minus 1. So this is actually the answer for part B. For factored form, part A, we can list the zeros as x equals 1, x equals negative 1, and so 1, negative 1, and then positive 3. But notice we have another negative 1. So x equals negative 1 has multiplicity that's even, because there's 2 of them. So at x equals negative 1, I'm going to say that here it bounces. The other 2 it's going to cross. So those are the zeros for part A. This is the factored form of the polynomial for part B. Now for part C, we need to sketch the graph. So the other 2 things we need to sketch a graph, remember, besides the zeros, we need the y-intercept. So if we go back to the beginning form, if all the x variables are 0, that's going to leave us with a 3 as the y-intercept. And then we have 1, negative 1, and positive 3 as our zeros. And then the end behavior, since it's at degree 4 with a positive 1 as a coefficient, means the left and the right side are going to infinity. Now starting here on the left, when we get to negative 1, because it had a multiplicity that was even, it's going to bounce. So negative 1 is going to bounce, go up to the y-intercept, and it comes here, and it crosses through at x equals 1. And because we have a gap that contains a whole number here, we need to place a point somewhere so that we know a little bit of an idea of how far down it goes before it turns back up. So we need to plug 2 in for all the x variables. And you can do it in the factored form or the general form. I'm going to do it here in the factored form. 2 minus 1 is 1. 2 plus 1 is 3. 2 minus 3 is negative 1. And then 2 plus 1 is 3. And these multiply. So 1 times 3 times negative 1 times negative 3, that's negative 9. So we go all the way down to negative 9, which is about right here. So 2 comma negative 9. And then it comes through at x equals 3, it crosses through and connects up right up there. Okay, question 7. This is from section 3.6. The steps that we had in class. Step 1 were to find intercepts. Step 2, vertical and horizontal asymptote. And then step 3, plot a few additional points. So let's do intercepts. Now I'm going to write r of x where the numerator and denominator are factored. So the denominator, x squared minus 9, that's x minus 3 and x plus 3. And then the numerator, 2x squared plus 3x minus 2. Let's see, 2 times negative 2, that's negative 4. So we need factors of negative 4 that add to 3, positive 3. So that's going to be 4 and negative 1. So I'm going to take the numerator 2x squared and split this middle term, 3x, into a combination of those two numbers, 4x minus 1x. So plus 4x minus 1x minus 2. So group the first two terms together, you can factor out a 2x, that leaves the x plus 2. And then when you group those next two terms together, you can factor out a negative 1, that also leaves you an x plus 2. So you have an x plus 2 in common, so you can factor out an x plus 2, which leaves you a 2x minus 1. So that factors into 2x minus 1 and x plus 2. Okay, I'm going to do the y-intercept first. So the y-intercept, we find that by letting x equal 0. Now, rather than using the factor form that I just created, go back here actually. If all the x variables are 0, we're going to have a negative 2 over negative 9, which is positive 2 ninths. So 0, comma 2 ninths. That's pretty much 1/3. So 0, comma 1/3, about right there. Now the x-intercept, or intercepts, there could be more than one. We find those by letting y equal 0. So if this is equal to 0, the only time a fraction with a numerator and a denominator is equal to 0 is if the numerator equals 0. So for the x-intercepts of a rational function occur when the numerator is equal to 0. That's going to happen at x equals negative 2. So that's negative 2 comma 0. And then from here it's going to happen when x equals positive 1/2. So we have negative 2 comma 0 and positive 1/2 comma 0. So those are y-intercept and x-intercept. Now the vertical asymptote is the domain restrictions. And that's why we wanted to look at it in factored form. Here, remember the domain restriction is when the denominator is equal to 0. So the denominator is going to equal 0 when x is 3 and when x is negative 3. So that's exactly where we place our vertical asymptotes, at those domain restrictions. So x equals 3 and x equals negative 3. So here's where x equals negative 3. And that's where x equals 3. Now the horizontal asymptote we compare the degree of the numerator to the degree of the denominator. If they're the same degree, which these two are, this is degree 2, that's degree 2. If they're the same degree, you find the horizontal asymptote by dividing the leading coefficients. So in this case, it's 2 divided by 1, which is 2. So the horizontal asymptote is the horizontal line, y equals 2. So this is where y equals 2. That's our horizontal asymptote. Okay, now we need to piece together the graph. And what I suggested you do is wherever you have a vertical asymptote, just plot a couple of points on either side of it. So we have a point here. Let's plot a couple of points over here. And then we'll do the same thing here. Maybe let's plot a few points over here and plot a few points over here. So if we have a table of values, I'm going to do a table of values for over here. So this is where x equals negative 3. So let's see what happens when x equals negative 4. So if you plug in negative 4 for all the x variables, you're going to get positive 18/7. And that's just slightly bigger than 2, so 2, maybe 2.4, something like that. So it's been right there. What that tells us is that entire piece of the graph is up above that horizontal asymptote. Just that one point is good enough for us to know that that piece of the graph looks like this. Now in between x equals negative 3 and x equals positive 3, we actually have a pretty good idea because there's 3 points already given to us. That piece of the graph looks like that. So now we need to plot a point or two over here on this side where x equals like positive 4. So we're going to plug in Let's do a new table of values. Let's plug in x equals positive 4. If you plug in 4, you're going to get 42 over 7, which is 6. So 4 comma 6. So that tells you a piece of the graph is going to look like that. Now the domain is very closely related to our two domain exclusions here. X cannot be negative 3 and x cannot be positive 3. But it can be anything else, so we write that as negative infinity to negative 3, negative 3 to 3, and then 3 to infinity. Question number 8, this is also from section 3.6, so we're going to follow pretty much the same steps. We're going to write this in factored form. So this is going to factor into x plus 3, x minus 1. Again, let's do the y-intercept. If we let x equal 0, then we're going to have a 1 and a negative 3, so negative 1/3. Just right about there. The x-intercept, or there could be more than one. The x-intercept is when the fraction is equal to 0, the function is equal to 0, but again, remember, in a fraction that happens only when the numerator is equal to 0, which in this case happens when x equals negative 1. Now, the vertical asymptote, there's actually two of them, or the domain restrictions that x cannot be negative 3 and x cannot be positive 1. So we put this vertical line as a barrier to say that x cannot equal this number here, and then another barrier here to say that x cannot equal that number there. And then the horizontal asymptote, we compare the degree of the numerator, which is degree 1, to the degree of the denominator, which is degree 2. And when the numerator has a lower degree than the denominator, the horizontal asymptote is always y equals 0. So there's our horizontal asymptote. Okay, so we're going to plot some points. Now I'm going to start here on the left. If we have a xy, we need to plot some points to the left of negative 3. So let's do x equals negative 4, even negative 5. Let's see what happens. So we get negative 3/5 when x equals negative 4. That's roughly negative 1/2, right about there. When x equals negative 5, we get negative 1/3, which is right about there. So what we can see from those 2 points, that piece of the graph looks like that. Now we have 2 points here. I'm actually going to see what happens when x equals negative 2 right here. What happens when x equals negative 2? And if you plug in negative 2 for all the x's, you're going to get positive 1/3, which is right about there. So what it looks like we have is something like that. Now over on the right side here, to the right of x equals 1, we can plug in like x equals 2 and x equals 3. So when x equals 2, we get 3/5, which again is roughly half. And then when x equals 3, you plug 3 for all the x, you get positive 1/3, which is right about there. So we get that shape. The domain, if we take out x equals negative 3 and x equals positive 1, we're going to have from negative infinity to negative 3, and then from -3 to 1, and 1 to infinity. Question 9 is a word problem, application problem from section 3.1. We talked about quadratics. So the maximum height, if this is the function that describes height, and you notice that this function is a quadratic function with a negative coefficient, meaning the function, the parabola is going to be upside down. And if the function itself describes height, then the highest point on that graph, which represents height, is the vertex. So the maximum height is the vertex. So we need to find the vertex. What I'd recommend, there was a formula that was taught in 3.1 that was the vertex formula. If you remember, it's the opposite of b divided by 2a. So in this case, the opposite of b is -64 divided by 2 times -16. So that's -64 over -32, which is 2. But you have to remember that the vertex only tells you the x value. This vertex formula, rather, only tells you the x value of the vertex. In this case, when I have an x value, we have t for time. So this formula tells you that the t value of the vertex is 2. And if t stands for time, then this formula tells us that the vertex occurs when the ball has been in the air for 2 seconds. That's when the maximum height occurs. We find the maximum height by plugging 2 in for t. So 2 squared is 4 times -16, that's -64. And then 64 times 2 is 128. So that's 64 feet. So that's actually the answer to part B. How long does it take the ball to reach its maximum height is the answer for part A. The maximum height is 64 feet. And then how long does it take for the ball to hit the ground? So this parabola is thrown from ground level. So there's actually 2 times this ball is going to be on the ground. It's at the ground when t equals 0, because initially the ball's at ground level. So how long does it take for the ball to leave the ground, reach its maximum height, and then come back down to the ground? Well, the ball hits the ground when the height is 0. So if we solve for t when h is 0, the height is 0, we're going to have -16 t squared plus 64 t. Now we can solve this one of 2 ways. We can use a quadratic formula because this is a quadratic function, or since there are only 2 terms, we can maybe factor out common factors and write it in factored form. So we can factor out a -16t. That's going to leave t minus 4. So what this is saying is that the height is 0 at 2 values of time. And the 2 values of time are when t equals 0. That's initial value, which we knew was correct because the ball started at ground level. So at initial time, the ball is at ground level. And then at time t equals 4, the ball is at ground level. So it took 4 seconds for the ball to leave ground level. It took 2 seconds to reach the maximum height, which we found in part A, and then another 2 seconds for it to fall back down, for a total of 4 seconds for the ball to hit the ground.